We're now going to become a set on demo on 3D mapping. So I'm logged in on the Xios, which is the front-end machine. I'm going to go now in the ROM's mapping directory. And in here you will find a new tutorial which is called main 3D mapping. So I'm going to open that. This tutorial has 5 components. The first component regards the vertical coordinate system of the model, which is a S coordinate, or if you like, terrain following coordinate system. So let's begin with the first tutorial. And in order to do this tutorial, we are going to load a specific grid, in this case the Northeast Pacific grid. So I'm going to go in another window now and go inside ROM's mapping. I'm going to run MATLAB, and I'm going to load my GRD array. Now, as you know, the vertical coordinate system is a three-dimensional field in that the depth of the coordinate system varies in space, but also in three-dimensional space, but also in time. And that's because the vertical coordinate system is also a function of the free surface. So in order to compute the vertical coordinate system, we also have to provide a free surface. So in this case, I'm going to load an output from ROMs for this particular Northeast Pacific simulation. And I'm going to load the free surface associated, say, with record number 10. Okay, just you can pick any one you want. Okay. At this point, I'm going to compute the depth of the S coordinate system, and using this function called RNT setDepth. This function wants 2 arguments, the free surface and the grid, GRD, and it provides 3 outputs. The first output is ZR, which is the depth of the vertical coordinate system at the row points in the vertical. And then there's ZW, which is the depth of the coordinate system, the vertical coordinate system at the W points. And then HZ, which is the thickness of each vertical coordinate layer. Okay, so let's start with ZR. And ZR is, if you like, the row grid in the vertical is it represents the mid depth of the layers of the model. Okay, and so it contains, in fact, in this case, n elements in the vertical. Anyway, let's just load this. Okay, and let's go in the other window, and I'm gonna, do this. I've loaded it, and now just for fun, let me just plot a particular subsection of the model, vertical coordinate system ZR. So I'm just going to go here, and I'm going to open a figure. I'm going to put it up here, and I'm just going to plot let's see, oops, for some reason I didn't paste correctly in MATLAB, and that's because there's a mistake here. You can see here. Okay, so we've corrected that. So let's grab this stuff here, and let's do that. And now let's plot the vertical coordinate system using this function called RNT plot sigma, which has as argument the ZR, which is the coordinate system, and then these other elements. This is the distance, is basically the x-axis that I want to on the plot. The I and j range and the s range, number of coordinates in this case, is going to be 1 to GRDN, which is every single layer, and then the color, which is K, black. Okay, so I plot that, and so here's now my ZR grid. Okay, you can see that obviously you find this is a sloping topography of some sort, and then there's some kind of abyssal plane here which still has some topography. You also find that this mid depth of each layer, that this is the depth, basically this line represents the mid depth of every single layer of the model of the 30 layers. You could see that there's it's very black, but at the surface is more intensified, and that's because the stretching parameters that we selected, if you look at grd.theta surface, we find that we have a high resolution at the surface, and at the bottom we have moderately increased resolution. Of course, I could change these parameters. For example, suppose that I make the surface not very resolved. I just give it a 1, and I make the bottom more resolved. Say I put 1 over there, and then I recompute the depths, and then I plot them. Let me just plot them with the different colors, say in red. you could see that now you get a different type of spacing in the layers, and they're no longer, you know, as the ones that we just saw. We could also select a more uniform layer. For the surface, we could use very mild resolution like 0.1. We can clean that. We can compute the depths again, and we can plot them. And actually, let's plot them in black. Okay, and so now you can see that there's a more uniform spacing, you know, of the layers. They're more uniformly spaced. Okay, so now we have that, and on top of this, we can plot now the ZW, which is the W grid in the vertical, and I'm going to plot this in green. And you can see that there's some staggering of this grid as expected. I'm going to zoom on here to show you even better this staggering. I'm going to start from the bottom here, and let's say we staggered here. And so what you see that this green layer here, this is the bottom, okay, and then the layer, the depth of the layer in volume is enclosed by this layer, this green layer here, and this green layer here, where the black, the ZR array at this particular layer, which is layer 1, represents the mid depth of this particular layer. In fact, this green line in ZW, which represents you know, ZWIJ1, okay, this in fact corresponds exactly to the bottom topography, and we can visualize that by just plotting also the bottom topography. I'm going to plot it as a blue dashed line. In this case, the S range is only equal to 1 because the bottom has no third coordinates. I'm going to put minus grd.h. Okay, and so you can see in fact that the bottom exactly tracks ZW of 1. Okay, now remember that in the ROMS convention, if you have a three-dimensional array, number 1 here corresponds to the bottom layer, whether if we put grd.n, this corresponds to the surface layer. Okay, so that's something to keep in mind. In fact, if the surface layer for ZW, the W point, let's zoom out here. Zoom out. Okay, and then zoom on. Let's go and look at the surface layer, something like, for example, here. Okay, and okay, and let me plot again the ZW. And now here I actually forgot to do something because ZW actually has n plus 1 points, so the S range is actually this one. And if you do that, you find that now there's this surface layer, and this particular surface layer here corresponds exactly to the free surface. And in fact, we can now plot on top of this the free surface as a as a blue dashed line. Okay, and you find that in fact this topmost layer is actually the free surface. Okay, and so now you have that the topmost layer for ZR, this black array here, is actually, you know, not exactly the free surface, but it's the depth, is the mid depth of this layer that goes from the free surface to down here to this green layer. Now this thickness here, okay, if you want to know what that thickness is, that's actually given by the array HZ in here. Okay, so HZ now has also 30 elements, and it basically contains the depth of every single layer. So for example, HZ, you know, of the surface HZ represents this depth, and you know, you have the second one represents this depth, and so forth. Okay, so that means that if we add up all the HZs, okay, all the way to the bottom, we actually retrieve exactly the bottom topography. Okay, because if we do a zoom off, zoom out, you can see that basically if you add every single layer, you stack them all down, you know, you basically get the bottom topography. So in other words, if we do sum of HZ comma 3, okay, this particular array should be equivalent to the depth to the bottom topography H. So we do that, and then we can clean this, plot grd.h. So this is the actual, oops, sorry, I did a mistake. We want to only plot ij. Okay, so this is, for example, the bottom topography here, and is the total depth of the water column, and if I plot now you know, the h that I computed through the sum in red, okay, you find that they're exactly identical. So this actually gives a nice relationship, because now you know that the sum of hz, okay, in 3, okay, so the vertical integral of hz in S is actually the depth of the water column. So that means that, for example, if we load, for example, the u velocity field, and let's load this, RNT, actually let's load the temperature field, temp equals RNT load var of CTL, comma 10, comma temp. Okay, so this is now the temperature, and if I want to compute the vertical integral of the temperature in the S coordinate system, okay, then I can just do temp. I can multiply that by hz, and then I can just add up, you know, the third dimension, okay, and this is going to be temp temp sum, okay, or actually this is temp vertical integral equals this thing here. So this is an easy way now to compute the vertical integral of a quantity, and I can plot that PLCM of this vertical integral, okay, and so now you see it's very high. I can divide that by the depth of the water column, of course, so this would be divided by grd.h, and this would give me the average, the depth average temperature, you know, in the domain, okay. And so of course you find that close to the coast, you know, because the water is shallow, you know, the depth average temperature is more close to, say, you know, warmer values. Whether if you go in the deeper ocean, you know, you find that the depth average temperature is actually colder, especially in the north, where, you know, we know that waters are colder. Now, to see that this is an exact transformation for the, now actually let's keep in mind that when we do the vertical integral, now we are no longer in the S coordinate system, because we have, you know, averaged that out. Okay, so that's actually equivalent of taking the vertical integral in the Z coordinate system. In fact, we can check whether these numerics are exact by loading, for example, the depth average velocity in the model, which is u bar, RNT load var of CTL, comma 10, comma u bar. Okay, so this is the depth average velocity field in the zonal direction, and if we plot this, we find that it has something that looks like this. Okay, now we can recompute that by just loading, for example, the three-dimensional velocity u. Okay, and then I can actually take the depth average of this velocity u sum equals, for example, u dot hz. Okay, and then we take the sum, you know, in the third array, and if I execute this command, it's going to give me an error. Okay, and that's because hc is actually in the horizontal is on the row grid, whether u in the horizontal is on the u grid. So really what I need to do is I need to compute hz on the u grid, and there's a transformation which is given by this function RNT to grid, and I'm going to say that I'm going to move hz from the row grid to the u grid. Okay, this is just a very simple averaging procedure, and so now I can compute h sum, but I use hzu. Okay, and this is an exact transformation, and now I only need to, I can plot this again, this u sum, and if I look at the structure, you find, you know, that it's basically identical to the u bar, although you can see that the values here are very high because I have to divide by the topography. So let's say that I have to divide by the depth, so hu is equal RNT to grid of grd.h, comma, I'm going to move this from the row grid again to the u grid. Okay, and now I'm going to RNT PLCM divided by HU. So this is the actual depth average velocity field, and this is how it looked like. And we can take the difference now with the U-bar, which was contained in the model. Okay, and you should see that there are some differences, and which is not very good, uh, but um, um, but that's also, keep in mind that this is an average file, and so there's some averaging that took place, which I'm not doing properly here. Okay. So anyway, so this is all for this tutorial, and we'll go. That's it. Thanks.